Hi, I'm Andrew Atherton.
I'm Tim Johnson.
I'm Brandon Leong.
I'm Mark McGarvey.
This is the manufacturing process of adiabatic expansion nozzles. The needs for our project were to create a similar extinguishing nozzle that was similar or reduced in cost. We needed to also reduce the production time from the current 5+ hours to about an hour per unit. We also wanted to maintain or exceed the current reliability and be able to put out fires with at least the same efficiency as the original methods or even faster. The motivation behind this project was that the stakeholder holding the patent was a retired FAA engineer. It's a good product to use in production, but it's time restricted and the production method is super cumbersome. We also wanted to get closer to taking the product to market. The end goal was to be able to mass produce the nozzles in an efficient and timely manner. So our primary stakeholder is retired chemist Robert Philipczak, the creator and patent holder. Other people who could use this product are police officers, firefighters, first responders, and small business owners. Current production of the nozzle takes 5 to 8 hours per unit. It's unorganized and it has high production costs and many errors. Production cannot be mass produced under these conditions. So our solution is to develop an efficient and reliable assembly method, reduce current production time by a factor of 10, and minimize production costs and labor by a factor of 10. Our approach had multiple methods. The first was to 3D print, the second a jig, and the third was to press fit all the parts together. We consulted various professors and machinists about proposed designs. Now I'll be passing the design description on to Andrew.
For our specifications, we are trying to make 5 units at once done on a jig in 1 hour and cut the unit price down to $80, factoring in costs of labor. Also, the nozzle must withstand pressures upward of 830 psi. Following are some standards that are used for the nozzle and manufacturing quality. Due to the virus and the pandemic going on, we're no longer able to do any physical work on our project, which was stopped right after the prototyping. Therefore, we weren't able to do any of the physical tests that we had planned, including drop tests, flow tests, and putting the nozzles on real fire extinguishers to see how they worked. Going over the concepts that we came up with, the 3 that we talked about were 3D printing the nozzle, making a jig to be able to put all the parts together more efficiently, and doing a press fit to avoid having to solder. For 3D printing, one of the pros is that with many printers, we can be doing many of the nozzles simultaneously. One big problem is they take a long time to make one, taking upwards of 5 hours to make just a solid cube without any of the complexity that the nozzle would require. For the jig method, one big pro is that we can have one jig that has a number of different stations, meaning that we'll be able to make multiple units at one time. But the big con to that is it still requires soldering, which can be tedious. These 2 pictures are models of the jigs that we designed, first being just the plate without any pegs in it, second being pegs that will hold the parts of the nozzle before soldering. For the press fit method, This big pro is that it avoids using soldering, which, like I said earlier, is very tedious. But for a big con is the wall thickness of for threading the end caps on is too small in the current materials that we have, therefore it will have to increase the overall size. This is a breakdown of adjusting the diameters of each tube, which will overall increase it more than 2 times the current model. So the method that we selected is going to be using the jig. So what we did is we took aluminum material to make the jig out of. Aluminum was selected because solder will not stick to the aluminum if it were to, say, drip onto one of the pegs as we were putting the nozzle together. Then a series of holes were drilled into the flat aluminum plate and pegs were put into them to fit the spacers on and the tubes simultaneously. Following is a CAD drawing of our plate with the dimensions for where all of the holes went. Now, as a prototype, we didn't fully finish making our prototype. This is just the aluminum plate that has the holes drilled into it. But if you direct your attention here, we have an animation of where the nozzle would be going. So first we have the center tube come down into the center, and then we put on a set of 3 small spacers, which then holds the next tube a certain distance away and centers everything. Then the next row of spacers, as well as the next tube, and then this process gets copied one last time. So now I'm going to pass this off to Timothy to go over the discussion.
So the first thing we have to look at in the discussion is, were the specifications met? So with the testing that we were able to do with the prototype, we did reduce the nozzle production speed. This is just by default. If we can have 5 nozzles being made at one time, that cuts it from 5 hours to 1 hour per nozzle immediately. We did not get to make a nozzle because all physical production was halted at the end of last term. So we made the jig prototype, but we did not get to construct a nozzle on it. The price of parts was roughly $75 per nozzle. This can be reduced by purchasing parts in bulk. Ours were very specific order, and they were even out of stock on certain things, so we had to order more expensive parts. And it also depends on labor costs. The last thing is seeing if the nozzle can withstand the 830 psi that the original could, that the CO2 tank outputs. Since we couldn't make a nozzle, we also couldn't test to see if it could withstand it. And doing a simulated test on a CAD program doesn't really help us, because we are looking for imperfections in our design that would cause a failure. And theoretically, we already know that the nozzle can withstand this, because Mr. Philipsak's original model was able to put out fires, and it could withstand the pressure coming from the CO2 tank. Next is the prototyping experience. The first thing we notice is that working with professionals is a key to making a good prototype. In the fall quarter, the first thing we did when we realized we might be cutting out things with metal is we went to the machine shop and talked to Mark Scheiber about, first of all, can we machine our design? Is it something that's possible to do? And then next, we asked him for feedback on the design, and is there anything we can change that would, make it easier to construct and easier to cut out. And we also consulted him on things like threading the nozzle, which helped us decide that our one concept wasn't going to be able to work because our parts were too thin. The next thing we learned was that you should always double check your dimensioning. The first jig we constructed went off of the patent dimensions, and those dimensions were not the actual size that the nozzle made out of brass that was using. So we had to redimension it based off of the physical prototype that we had from Mr. Philipzak instead of the official dimensions in the patent. Next was the analysis. So since our prototyping was halted before we could make a physical nozzle, we were unable to do any of these tests. The first was the drop test. This was going to be having the nozzle at a high height and dropping it and seeing if it can withstand the fall, measuring things like the forces that it experiences. This would simulate everyday wear and tear on a fire extinguisher, maybe dropping it from a countertop, or if it's in a car, maybe falling out of the car or rolling back and forth and hitting the car walls. The next test was a flow test. This was going to be conducted by calculating either the mass flow rate or the volume flow rate of the outcoming flow from the nozzle. And this was going to be compared to the mass flow rate from the original nozzle to see if we can either meet the same mass flow rate or exceed the desired mass flow rate. And the last was to do an actual fire extinguish and work with a local fire company to see if this nozzle actually works. The reason that we couldn't do these or even simulate them is because they needed a nozzle that we had hand created, so it would have any common design flaws, things like the solder knot, welding and mating with the cylinders, things that would cause it to fail. And it's hard to simulate these in software because you can't really design in imperfections. And since we're not creating a new nozzle, we already know that the nozzle is going to work, and we're trying to see if our new production method works or not. And next, I will be also talking about the methods. So the first thing is the materials. We purchased flat and round stock aluminum that we used to create the jig. The rest was purchased by Mr. Philipzak and given to us to help in our testing. This included brass tubing and end caps and the tin solder and flux that we used. Next is the fabrication methods. We spent most of our time fabricating in the machine shop. First thing we used was the end mill to drill holes into the aluminum plating. Next was the bandsaw that we used to cut the aluminum rods down to the length that we needed them. And the last was the lathe that would turn the aluminum rods down into the pegs that we could place in the holes in the jig. The software we used was for CAD, mainly Autodesk Inventor. We used this to design the jig and make the animations of the nozzle assembly using the jig. And we also used Microsoft Excel to calculate wall thicknesses and expansion factors when we were testing the idea of doing a press fit, knowing that we would have to make the nozzle bigger. And next I'll be handing over to Mark to talk about context and impact.
So as far as economic impacts for the design, the nozzle costs less than a traditional CO2 fire extinguisher. These extinguishers typically cost around $200 plus. As far as environmental impacts, using CO2, there's no harsh chemical reagents that can be used to extinguish the fires compared to a halogen agent, which has a negative impact on the ozone and other negative environmental impacts. As far as social impacts, the use of the assembly line process with the jig will produce additional jobs, and the nozzle will be able to be used by both first responders and civilians. As far as ethical impacts, the the extinguisher must be reliable and efficient in extinguishing the fires, because if not, it will cause significant harm to the operator. It also must bring a peace of mind, knowing that the fire will be extinguished without ruining appliances or equipment. Now I'll cover the summary and conclusions. We found multiple proposed solutions for the problem, and when we presented and received feedback on the solutions, through our feedback, which was that we did not have many modern manufacturing methods such as 3D printing. We investigated these, and also additionally with the 3D printed, we investigated a press fit method. We determined through our investigation of all these methods that the most viable solution at the current time was the jig method. As far as things that went well, the handling and addressing of the presentation feedback of the use of modern manufacturing techniques went very well in our research in those methods. Physical prototyping and machining also went well with our experience in the machine shop and our help from the workers in the machine shop. The winter poster session and prototype presentation also was extremely useful, with feedback from the faculty in relation to changes we can make to our project. The challenges with this were finding a group in a project early in the year, spending time researching all the different methods, and not enough time designing our specific method, which was the jig. As far as lessons learned, the first one is to find a group and project way before senior design starts. Specifically, look for one maybe in your MEM 391 course. Focus on one solution that works. Do not spend too much time testing other methods. Practice presentations early and often to make sure everything works. Maybe specifically practice presentations in the place you will present it in. Our videos in the fall presentation took a while to start loading and cost us about a minute's worth of time. And do not trust one source for dimensions. We used the patent, and the dimensioning on the patent was incorrect for the actual parts we had. As far as recommendations for rising seniors, again, find a group and project at the latest winter, spring of junior year. Talk to your professors about any project designs or ideas they might have, and delegate the responsibilities early and establish a project manager who can keep you on track with all the deadlines. Stay connected with your stakeholders and get feedback based on the decisions you're making at the current time. Start designing and prototyping as early as possible so you can find flaws in your design and fix them. And work with the machinists in the machine shop. They have many years of experience and know what they're doing and have very good solutions to your problems. And now I'm going to pass this over to Brandon so he can talk about the project management.
For our project, we had no fixed budget from the stakeholder. Nozzle parts were already provided, and the total cost of those parts was around $22,000. We received about enough parts for around 20 prototype assemblies. The only parts that needed to be purchased were the materials for the jig, and they were all purchased from McMaster. The total cost of the parts was around $75. Due to the COVID epidemic, we had to change our project timeline, and we just had to meet certain deliverables by certain dates. So the first thing that we had for the spring term was the state of the project, which was addressing the issues that the pandemic affected, and then the final report, and then finally their presentation. The video summary, the draft websites, and everything else were optional, which will be done separately.
Lastly, we would like to say thank you to our senior design advisors, Dr. Yablokov, Dr. Auerbach, the person who organized senior design this year, Dr. Atchison, our stakeholder, Mr. Philipzak, and Mark Schreiber and the other machinists in the machine shop.